10.5 is hyperbolas. It's our last conic section to cover. Remember, an ellipse was the set of all points where the sum of their distances from two foci was constant. A hyperbola is the set of all points where the difference of those distances is constant. So let me show what that means. Here's a hyperbola. It's got what looks like two parabolas. These aren't actually parabolas. These shapes here aren't parabolas, but they kind of look like it. And it's got a vertex here and a vertex here, and a focus here and a focus here. So two vertices and two foci. Here's some point on the hyperbola. The distance from here to here is dB, 5.33. The distance from here to here is dC, 10.74. And as this point moves, you'll see these points both decrease. I'm getting closer and closer and closer, and their values decrease. But this one stays constant. The difference of the distances is always the same, 5.4, 5.4, 5.4. And I could have grabbed this point and dragged it all the way to this side also, do the same thing along this curve, it'll work out the same. As the foci move closer and closer, the hyperbola gets kind of warped a little bit. As you move it farther and farther apart, it warps again. You'll see it better if I move this foci around actually. Here it spreads wider, 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 wider. Here they get closer, 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 until it's just stretched really, really tight. For just a split second, it becomes a line. You can't really see it. And then at this point, they're becoming ellipses, but that's because of how I built this. So you can change the orientation of these hyperbolas, and you can change the way they look. So if I bring this in closer, 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 it's going to become an ellipse again. And if I bring it in all the way, it's actually a circle. Then back out, here's our hyperbola. If you think about our last chapter, these were called hyperbolas. Here's the graph of 1 over x. This is a hyperbola with a center here, vertices here, and then foci somewhere in this range. Here's an example of a hyperbola with horizontal orientation. The vertices are these vertices here, basically. These points here aren't actually called co-vertices. I shouldn't call them that. In fact, I'll delete that right now. But there's still your horizontal A distance and your horizontal B distance. So from the center to a vertex is A, so all the way across is 2A. The points A, B, and C are still in use. Here's A, here's B, here's C, just like they were with ellipses. And here is all the equations and formulas we can use for these hyperbolas. So I'm going to graph this ellipse right here. What matters with ellipses isn't A or B. I'm sorry, with hyperbolas. What matters with hyperbolas is not A or B. A or B is what mattered with ellipses. But with hyperbolas, what matters is which comes first, the x or the y. If it's x minus y, it's going to be a horizontal hyperbola that looks like this. If it's y minus x, it's a vertical hyperbola that looks like this. So this one right here has an x value that comes first, which means we know it's going to be a horizontal orientation. And just like before with ellipses, A and B stand for distances. Don't think about them as points, think about them as distances from the center. Every hyperbola we graph in this class will have a center of 0, 0. Well, my A value is 3, and my B value is 2, so you always do the square roots of these things over here. You always do the square roots. So, from the center, if I go left and right 3, and up and down 2, those are my horizontal and vertical distances. Whatever number comes beneath the x variable moves left to right. Whatever number comes beneath the y variable moves up and down. And then I do this kind of weird but sort of nice little thing. I'm going to draw a box. And this box is going to contain the 4 points that I just graphed. The 4 points that I just graphed are contained in this box. The next thing that happens is I draw lines. And these lines connect from the corners of the box. Take this line and extend it this way. And I do the same thing going this direction. And at this point, I've really done all the work that I need to make my hyperbola. It's going to involve these two vertex points, these vertices. These are 2 points actually on the graph. And then the hyperbola curves out towards these lines, and these lines are asymptotes. That's why it says asymptotes here. They're asymptotes that the graph gets closer and closer to, but won't actually touch. And there is my hyperbola. You draw your box, connect the corners of your box, and then figure out if your hyperbola is going sideways or up and down. It's really that simple. If you move around the center, had I thrown in an h and a k, it gets much more complicated, and we're not going to worry about that. We'll leave that for another time. So here, I've been given a hyperbola. I want to write its equation. Well, this hyperbola has a vertical orientation. It's pointing up and down. So I know it's going to be this formula over here. Y squared over a squared minus x squared over b squared equals 1. So now I've just got to find distances. And the distance from here to here is 3. So this is going to be y squared over 9. And the distance from here to here was 2. It's going to be minus x squared over 4 equals 1. If, and there's the equation, we found it. Found my a value, I found my b value, I've got my equation. If I had been asked to find the foci, we haven't talked much about foci. Those involve the c coordinates, and hyperbolas use the good Pythagorean theorem. Ellipses use the evil Pythagorean theorem, a squared minus b squared is c squared, but here we use the good one. So to find c, well, no, c squared is a squared plus b squared. So c squared is 9 plus 4. So c squared is 13. So c would be the square root of 13, which is 3.4-ish, I think. I think it's about 3.4. Let's just say it is. So my foci would be up 1, 2, 3. I don't know if quite so right anymore. Because this was actually distance of 4, not 3. Pardon me, that was a distance of 4, which makes this a 16. So I'll find the square root. About halfway between 4 and 5 should be about 4.4, I think. 4.47, let's say 4.5. So from the middle, I'll go 1, 2, 3, 4.5, and down to 4.5, and those are my foci. Parabolas, circles, and ellipses always have a focus inside the curve. Wherever that curve is, the focus is inside it. Okay, they always have a focus inside the curve, in this case 2 foci, inside the 2 curves. We'll do another one. Now look, this one right here has the same exact box as the one over here. This box here is the same as this box here. The only difference is this one has a horizontal orientation, not a vertical. So all I'm going to do is switch x and y. I get x squared over 4 minus y squared over 16, and that's equal to 1. I think that should pretty much take care of it. If you have any questions, let me know. Nice and short today.